there's also something, sorry, I don't know what, well. Okay, there's also something else that makes these microRNAs interesting, at least to me. I'm a big fan of weak interactions, so maybe that's why I like this problem so much. So you imagine again that you have a microRNA and that's regulating two messenger RNAs or two RNA molecules, doesn't matter which ones. And you ask yourself the following question: how much can I tune the level, how precisely can I regulate the level of this RNA by playing with the level of the transcription factor that controls the first RNA, okay? And I measured that with the mutual information between these two things, right? Again, you imagine you have a stochastic simulation, right? So you have probability distributions in the steady state, and you can measure the mutual information between these two things as functions of parameters, right? And I want to compare this with the mutual information that exists between the transcription factor of this RNA, which is the same as this, and this RNA itself. So I'm basically comparing how precisely I can regulate the level of RNA2 by playing either with the transcription factor of its competitor or with its own transcription factor, okay? Now, ideally, I mean intuitively, one would expect this channel to be a lot more efficient than this one, right? I mean, mutual information is basically about black boxes, so it doesn't really matter what's inside. But I mean, there's lots of noise that is being added as you move along this channel compared to this one. So this is probably more efficient. Yeah, and actually it is more efficient, right? So the mutual information that you get from this channel is basically the black line here. It's roughly constant, while the blue line represents the mutual information that you have in this channel. And here I'm plotting this as a function of a parameter that sort of controls two things. So as it gets smaller and smaller, this parameter means that the population of microRNAs is increasing, but the strength of interactions is decreasing very much. So here we have a lot of weakly interacting microRNAs, and here we have few very strong, very focused microRNAs, okay? And what you see is that as the interaction gets weaker and the population of microRNAs gets larger, these two channels actually perform equally well, okay? So weak interactions can be effective. It's just a matter of, you know, tuning some parameters, and then you can do quite a lot with them. You can do quite as well as you do with transcription factors, with microRNAs.
Sorry, omega is a sort of ratio between number of microRNA and binding affinity towards the target region.
Omega is a parameter that multiplies the binding affinity and the degradation rate of microRNAs. Okay. So if it gets smaller, microRNAs live longer and interact more weakly. Okay? But you can do this in many different ways. Yeah. You can tune it, it's always the same. Okay, so what we thought about doing is, well, you know, this is interesting, right? Because if you try to look at the data, how strongly microRNAs interact, what is known about this, we started actually from a very well-known database that is called TargetScan, but in the end we dumped it, we used it as a backup actually. I would just talk about this data. It's called, coming from a Cell paper in 2013, I think. I will just call it the clash data for simplicity. Clash is a technique, it's a biochemical technique that basically gives you a picture of who microRNAs are bound to, okay? And they did it extensively, and they reconstructed some of the links. These numbers that are given here are actually taken from the data that come with this paper. They are not very large networks, so it's not like transcriptome-wide, they're fairly large. So 7,000 RNAs, 800 microRNAs, and about 20,000 interactions, right? So it's a relatively diluted network. But the nice thing about this paper is that they classify a lot of interactions, actually all the interactions, in terms of how they interact, because that's a biochemical technique. So there's a lot of information there. So this kind of interaction that I call K-mer, well actually they call K-mer, is the sequence-specific one that I showed in the movie in the beginning. So you try to match the sequence of the microRNA to the sequence of its target, and these are the strongest interactions. There's a seed region, there's a binding site, that's where they have to match, and these are, right? And basically they constitute the last 3 bars of the, so this is just a histogram of the different types of interactions that you find in this data. So the sequence-specific ones are just the last 3 bars. So they sum up to about like 17% of the interactions. Let's say 20%, okay? Here. All the other interactions that they found are not of this type. So either they have mismatches, or they have bulges, or there's some complex configurational change going on, or they're not even specific at all. So they don't just electrostatic, okay? Just imagine lots of electrostatic interaction. Actually, more than 20% of the interaction, they don't seem to have any sequence signature.
Andrea?
Yeah.
How long are the microRNA?
About 20 nucleotides. And the typical binding site is 8. Sometimes they bind with 9, sometimes bind with 6. Okay, you can imagine this is also a scale for how tightly they bind. So these are much stronger interactions than these ones, okay? But there's lots of these ones, like 80% of the interactions are of this type. Okay, so clearly what you expect is that because the silencing job is highly specific, you have to bind the molecule and you have to stay there bound long enough to silence it, okay? These are the ones that take care of the silencing, mostly. Well, these ones can also do a little bit of silencing, right? But they're not as efficient as these ones, as the other ones, as the specific ones, okay? But both of them, they can modulate crosstalk, okay? So
are you sure that low affinity binding can do silencing at all?
okay, that's actually a very good question.
Because I was under
In the
impression-
beginning, so the reason why we discarded the target scan database is because it was constructed originally with the assumption that low affinity binding doesn't do any silencing, okay? Now in the last iteration of target scan, which came out about 3 months ago or 2 months ago, they've changed it. And they started including non-specific interactions as well, because they saw that if they do silencing, they also do some silencing, okay? But I mean, I don't expect them to be as efficient as these ones in silencing, but they still will do that. Okay, so anyway, this thing, there's got to be a lot of crosstalk, right? So let's try to understand what it looks like. So the problem that we had is the following. So you can write down equations for how the levels of each molecular species in the RNA network, so in the microRNA RNA network, a bipartite graph, change in time, right? And what we want to calculate is the susceptibility, so how steady state levels will change when I perturb the transcription rates a little bit, and we multiply this by D for convenience, so that this becomes non-dimensional, adimensional, something, so we don't have to worry about units, essentially. So the thing is this, that after playing a little bit around with these equations and their steady states and what we want to calculate, we actually found an equation that allows us to compute the entire susceptibility matrix for any network, right? Doesn't matter the size, this is a simple numerical problem. And the way we did it is by brute force, essentially. So we just computed one derivative after another, and we tried to manipulate it either by hand or with Mathematica, and in the end we came up to this, and it actually works really, really well. So there's nothing fancy to say about this formula, really, it's just brute force. But anyway, this gives us a way to compute all these things for any of these networks. So we did it for Clash. Which again, to give you an idea, we have, because each of these indices, I and J, goes from 1 to n, we compute 7,000 square susceptibilities, and these are the number of, the numbers that are involved. In this
formula is correct if the system is up to two-body interaction, I guess.
No.
In general.
Yes. Yes. I'll show you. It actually allows you to decompose it. You can decompose susceptibilities in the paths microRNA mediated paths that separate two RNAs. I'm coming to that. Oops, what's that?
So independently of the non-linearities in the right-hand side, you find this.
Yes. Yes. This must have some meaning. I don't know. I'm not. I don't know.
Still, you're assuming the mean field approximation.
That's my starting point. Yes,
Okay.
that's my starting point. Yes, but you know, I mean, this is actually what I want, right?
Do you think that this might be, I mean, true even in the master equation?
See, the point is that I want to look at the competition-induced effects, not at the effects that are induced by fluctuations. So of course, if the level of a microRNA fluctuates, I will observe some response in the other targets, but that does not mean that if I perturb one of the targets, the other will respond. Okay? Because we are not in a case in which susceptibilities are symmetric, so there's no fluctuation dissipation theorem.
Okay.
Okay? So I actually want to focus on a deterministic case to calculate susceptibilities.
So a question, so this is about just silencing or includes the microRNA machinery to degrade, like
Yes.
the agonodes as well?
Yes.
Because is the concentration, for example, the limiting resources because you have finite amount of agonodes and so
Okay,
included
yes.
here?
No. So we assume that there's as much as argonaut as you need. So microRNA is always functional. Actually, I think there's indications that that is not a bad assumption. But you're right. It's actually not only argonauts. It's the whole risk thing
Right,
that
right.
we are.
Machinery of-
Yes, we have as much as we like.
Right.
And you can produce as many microRNA as you want. There are not like energy limitation.
Absolutely. Yes, I'm that powerful.
And what is W here?
Sorry. W is a matrix that is a very complicated combination of steady state concentrations and kinetic parameters. I can show you. Well, it's actually in the paper. It's actually in the supporting information for the paper, but I can show you later.